It's a pleasure to introduce Dr. Rita Bottino, who is going to talk about auto, allo, and xeno islet cell transplantation. Dr. Rita Bottino is doctor in biology, specialized in islet cell biology and transplantation. She is associate professor at the Institute of Cellular Therapeutics of Allegheny Health Network in Pittsburgh, and she's director of the islet program at Imagine Pharma. Dr. Bottino studied in the Department of Transplantation at the University of Genova in Italy, and she was training with Camillo Ricordi at the Diabetes Research Institute at the University of Miami. She worked also with Daniel Pipilers at the Diabetes Centers at the Bray University in Brussels. She joined the faculty at the University of Pittsburgh under the leadership of Massimo Trucco. The work of Rita Bottino involves clinical and experimental islet transplantation, including the first ever report long-term successful islet transplantation of genetically engineered pig islet in non-human primates. She is author of 127 published articles, and the last years, Dr. Bottino won the award Spirit of Network from Pancreatic Organ Donors with Diabetes. Thanks in advance for your conference.
Good afternoon. Let me tell you, it is my privilege to be participating in this meeting. Although it's virtual, it has a great, phenomenal program, and I wish really good luck and a productive meeting to everybody. It is my pleasure to talk today about islet transplantation and formalities about no conflict of interest, no financial disclosures about these presentations. I really would like to thank the organizer, Dr. Gorban de la Pertosa, Dr. Fuente, Dr. Valdes, for inviting me and for organizing this meeting. And I hope you let me say just a little word of thanks to my whole-time collaborator, Dr. Marcelo Perone, who we all remember from the time he was in Pittsburgh. And Marcelo not only brought his knowledge, his enthusiasm, but he brought the sunshine. So a thank as well to Mariana Sofia, and more importantly to Hannah, who is translating and who is helping me to communicate with you. I regret I cannot deliver this speech in Spanish, unfortunately, but Hannah will help us. And I regret more selfishly that I cannot be there, because visiting your country has always been my dream. But without too much ado, we're going to go and talk about islet transplantation. This is a field that you all heard about. And sometimes probably you wonder whether this is a real therapy, it is a myth, what it is. And although this is the area where I spent pretty much all my career, I hope that I will provide a balanced and objective overview of the field. Now, in islet transplantation, like in every field, like in life, is like allegory of life. The story of this important procedure is characterized by situations of up and downs, success, hopes, disappointment, but this is really life. And I hope that you will get a flavor a little bit in the next 30-40 minutes about this story. So the hard question is islet replacement an effective therapeutic options for patients? And I think the most important point of view, the one that I would like to start with, is the point of view of the patients. And quality of life. With the therapy that are available now, there's no question that insulin is necessary, saves lives, and gave life to patients that have type 1 diabetes or they have insulin-dependent diabetes. But the quality of life can be questionable. Patients have to face multiple daily injections, and I don't have to tell to this audience the risk of overdosing and hypoglycemias, but as well the risk of an insufficient glycemic control. And down the road, there is always the concern to develop secondary complications. Concerning secondary complication, we have learned from the DCCT that despite the use of insulin, despite a good control, patients over time face the possibility to develop secondary complications. And overall, the lifespan in these cases can be shortened significantly. And when the DCCT-EDIC was followed up, covering over 30 years of studies, once again, it was demonstrated that a good glycemic control, a good insulin administration can delay or can decrease the risk of secondary complication. But the secondary complication and the risks are there. So the goal of islet transplantations is to replace the pancreatic islet beta cells that are lost to autoimmune destruction, as in the case of type 1 diabetes, which we know is very specific destruction of beta cells, or because for various reasons, including, for example, presence of chronic pancreatitis. We'll talk about that later. The pancreas has to be removed. But islet replacement is something that is a little bit different than just re-established and endogenous insulin production. And we will look at that from a biological point of view now. So the pancreatic islets are complex units. We all know that they are composed of different cell types. The beta cells, which make insulin, represent the majority of the cells, but there are other cells that are part of the islets. And as soon as we have a community of cells, it's like a community of humans, things get complicated. And quite frankly, the attention has been given in the last couple of decades more to the understanding of how beta cells work, how they make insulin, how insulin is released. And that, of course, made sense because that's a fundamental function. But there are other cells that also have function. We don't really know very well. Even the architecture of the islets change. It is species specific. And even in our life, over time, the architecture and how these cells are connected with each other, they change. What do we know? We don't really know very much about the cells that are not beta cells. But now there is attention from the scientific community to understand more about the non-beta cells of the pancreas. For instance, I'd like to mention the studies on alpha cells that right now are becoming more common. Also because clinicians, you tell us that patients that have type 1 diabetes very often have a glucagon impairment. They have an impaired counter regulation. Why is this happening? What are the mechanisms that lead to that? I'd like to mention the studies of our longtime collaborator, Marcella Brisova and Al Powers at Vanderbilt. What they did, they studied the isolated islets of donors that have type 1 diabetes. We actually happened to isolate these islets, believe it or not, in the pancreas of donors with type 1, long-standing type 1 diabetes, there are still islets. And what is very interesting is that if you look at the insulin secretion in these type 1 diabetic islets and stimulate or inhibit insulin secretion, they act exactly as non-diabetic islets. But when they look at the alpha cells and they look at glucagon secretion, which is shown in this graph, what they found that actually the way the control non-diabetic islets behave in blue in this graph is different than how the islets in type 1 behave. So when it comes to glucagon secretions in type 1 diabetes, there is a weakness. In particular, the alpha cells do not seem to respond as effectively as normal islets to stimulation as well as inhibitory stimulation. Does this have a clinical relevance? I believe it does. But looking more into things that we had neglected. nowadays is very fashionable, is a la mode to say that beta cells are not the same. We thought they were all the same, but now we have evidence that they are not. They act differently, that one beta cell is different than the others. But this is actually an old concept that Danny Pupeliers in Brussels, with whom I had the privilege to work, had already discovered almost 40 years ago. When Danny was awarded the Minkowski Prize in 1986, he delivered a talk entitled The Biosociology of Beta Cells, which tells us that he had envisioned that beta cells are different and they probably have different functions. But it took almost 40 years before evidence was brought up. And what we know now definitely is that there is a difference in beta cells according to where they are located in topography, in their nuclear content, in their ability to respond to glucose, and even in the machinery that are in the membranes and in the cytoplasm. So we are just scratching the surface of what is known about the islet cells. Another big misconception, and this is a bias that often occurs in biology. Because C-peptide, which you all know as it is a biomarker utilized every day as a surrogate of beta cell function, because it is released together with insulin, for a long time, C-peptide was thought to be just basically an inert protein without any function. And the reason is because it's not very well conserved in evolution. So it's different from species to species. And the general concept is if something is not well conserved, probably is not very helpful. But it took a long time. But finally, thanks to the work at Karolinska of Dr. Warren, to test and to figure out that actually C-peptide is not a bystander, but has several activities, biological activities, including, among others, an anti-inflammatory effect. And even in vivo, in renal function, it has a protective role. And what I find extremely fascinating is that C-peptide seems to be in a sleepy, latent state until there is a stress. But in a condition of stress, that's where the biological activity occurs. And even more interesting, the protective effect of C-peptide, for instance, on stress endothelial cells, occurs when C-peptide is in physiological range concentrations. It doesn't occur if it's too low in concentration, and this may be logical, but it doesn't occur, protective effect doesn't occur if the concentration is too high, which can make them think about of patients when they are in the phase of type 2 in which they produce even more insulin. So there is still a lot to learn. But there is another story that I wanted to just tell you. This is a story of cross-fertilization between fields. So we all know that islet cells in the pancreas is innervated, and we know that insulin and glucagon respond to adrenergic and cholinergic stimulation from the central nervous system. But what we didn't know is what was happening within the islet itself. Zachary Freiberg is a psychiatric. He was at Columbia. He moved to University of Pittsburgh. And he's also a cell biologist. And he was very interested in understanding why his patients that are treated with antipsychotic drug, in particular clozapine, they quickly develop diabetes. I could not believe myself how, when he showed me data, and you probably are familiar with these patients, how quickly they develop diabetes. So by trying to understand this, he figured out that clozapine, these drugs, not only binds to the dopamine receptor in the brain, which is the effect they want because it's an effect that allows patients to feel better, but it also binds to dopamine receptors that are on the beta cells. Now, we knew dopamine receptors were there, but nobody knew why. But what he found is that dopamine is actually secreted and produced by alpha cells, and it can can be produced by the beta cells, as long as beta cells have the precursors, L-DOPA of dopamine. What is the role of this locally produced set of catecholamines of dopamine? Well, what is interesting is what the Spuina found. She found that dopamine actually stimulates glucagon secretions and inhibits insulin secretion. The overall effect is through locally produced catecholamines, there is a decrease in insulin secretion and there is an increase in blood glucose level. This is a very interesting mechanism, which in a way goes against what is the common knowledge. And what is interesting about this is that when they tried to present this work to diabetes community, everybody got very excited, but as a matter of fact, it's very difficult when you demonstrate something that goes against the dogmas that it is well received. So this paper actually is going to be published in a psychiatric journal, but it's going to have a huge impact in the diabetes field. So with this information that I hope I provided to you clearly, I do believe that from a biological point of view, islet cell replacement is different than just giving insulin and just providing insulin supplementation. So how do we do islet replacement? In two ways: pancreas, through pancreas transplantations, as well as islet transplantation. You may remember that probably around 10 years ago, it was very common during international meeting that at some point there was a debate where supporters of pancreas transplantation were discussing with supporters of the islet transplantations. And of course, this was based on scientific evidence, scientific discussion, but to me, a lot of time it looked a little bit like a reality. And I always felt in front of these debates that for a long time, quite frankly, the winner was the pancreas transplantation, and this mainly because of the outcome. But now I really have changed my mind, and I'll provide you some data later on that probably will have an influence on you as well. So what are the major characteristics? Pancreas transplantation is a significant major surgeries, and we know that at least in the first year there are important complications. But there is a lot of experience, and everywhere in the world there are excellent surgeons that can perform safely pancreas transplantations. When complications are overcome, typically there is a very good control of diabetes and very good control of glycemic levels. However, despite this, and irrespective of islet transplantations, if we look at numbers, pancreas transplantation is less and less performed. We have gone down from, in the United States, from 1,400 to 1,000 in approximately